Okay, now let's look a little bit at set theory. So we won't get into this in huge detail. And again, there's a set of slides that has quite a bit more information. One thing is just notation. So sets are just collections of objects, right? There's a few kind of basic things. So one thing is just notation, right? So let's just go through that real quick. So let's say I have this set containing 1, 2, 3, right? So that's one way of writing the set, right? I could write this with a description, and I could write the set of all x, say in the integers, so in Z, right? So this element, okay, so that's a good. Okay, let me introduce that in a minute. It's not in the best order here, but they could say the set of all x, and in fact, let me just do this. Okay, let me just back up there. Okay, so that's a set, right? So let's say that's the set A. Okay. This notation here, 1 is an element of A, just means that, right? So 1 is in that set. 1 is an element of A. 4 is not an element of A, right? Pretty clear. Now I'll just do a few more basic things here. So 1, 1, 2, 3, right, is exactly the same as 1, 2, 3, right? So there's no duplication of objects in a set, right? So like, even though this looks like it has 4 things in it, if I said how many things are in here, you'd say 3 things, because there's only 3 actual things. This is actually really useful in computer science. Like, you're going to count the number of words in a document, right? You can enter the entire document as a list, right? And then ask the computer to turn it into a set and say, how big is the set? And that's the number of distinct words, right? So this kind of trick is really useful. I could also write this way. I could write the set of all x, right? Such that x is in Z, right? So integers, and x is greater than 0, and x is less than 4, right? So, I mean, that's kind of silly, but this would be some expression like s of x, right? So I'm describing the set by a condition, right? The set of things for which this is true, right? And that will be exactly the same as this set here, right? So this is another way of writing A, right? So these are look very different, but there's one set A, right? Here is written by some sort of description, and here is written by just listing out the elements. When I have an infinite set, of course, I can't list out the elements. I have to write a description, or you have to kind of cheat. I mean, you can say things like set of all x such that x equals 1, 2, 3, and you use this dot, 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 right? So that's pretty common, but then this is really a condition that says you're looking at the set of all x, which is a positive integer, something like that, right? So it's really kind of cheating, right? But we do it all the time. An important thing about, I guess, an important set is the empty set. And so sometimes you write it like that, sometimes you write it like that. Really don't want to use that for 0, right? Because it really does mean the empty set. When key point about sets is that A is equal to B, if and only if. This is called extensionality. So for all x, x is in A, if and only if x is in B. Right? So again, I'm going to go back to this kind of silly example. The empty set is equal to the set of all x, y, z, right? Such that x cubed plus y cubed equals z cubed, where and x, y, z is an element of, z plus, right? The positive integers. Okay, so these two sets are the same because extensionally they're the same. I mean, they're very, very different and intentionally, right? This is a clear set to understand. It just has nothing in it. This is a set that, in order to understand that it's empty, requires, a 600 plus page proof, right? So I mean, the intention here is very, very different, but extensionally they're the same set, right? So in fact, math problems can just be expressed like this. Like, expressing that this set is empty is one way of just expressing Fermat's last theorem, right? At least for 3 there. So that's a thing to keep in mind, right? But two sets are the same if they have the same elements. That's exactly what you mean, right? And another way of writing this, right, and the way we often use this in a proof, so let me just introduce this notation. A is a subset of B, if and only if for all x in A implies x in B, right, like that. And so this expression here, we could write A equals B if and only if A is a subset of B, subset of B, and B is a subset of A. And so very often when we're proving sets are the same, we do that, right? We do it in a two-step proof. We prove that one set is in the other set and this set is in that set, right? Very, very common when you're doing proofs where you're trying to show two sets of objects are the same, which is a very common thing to do in math, okay? Let's see, there's a little bit of algebra to learn, right? So we have A intersect B, we have A union B, we have A minus B, right? So in pictures, I will just do that. So this is A, this is B, very common. These are Venn diagrams, right? A union B is a set of things in either. Oops, I did that so wrong. Fortunately, I'm on this thing where I can cut and move things. So I said it correctly, but what I wrote, so there, A union B is that one, right? A intersects B. I'd have these two things like this, and I look at the stuff that's in common, like that. Or, you know, the stuff that's in both, right? That's A intersects B, and then A minus B are the things in A and not in B, right? So like that. So that would be like A minus B. Okay. Sometimes we have a universal set, so we might have a universe U that we're looking at, and so we might draw our pictures like this with like a box around it. So that's like the universe, right? And then I could have A in here, and then I could have this stuff on the outside and call it A complement, right? And so we might, in that case, we might write A complement. We might also write neg A or not A or something like that, right? But it's kind of officially U minus A, but the U is kind of understood, right? So that happens a lot. Like if we're working everywhere, we're looking in the reals, right? And we want the complement of the interval from 0 to 1, right? So that's everything outside of 0, 1, right? We understand what that means without having to write R minus that interval. And one thing about these is they're very much like their um, propositional counterparts, right? So for example, we had this proposition that looked like, oh, let's see, I need one. Oh yeah, we have a proposition that looks like this, right? Not A or B, this is De Morgan's, right? Is equivalent to not A and not B, right? So in the set theory, right, this turns into the negation, right? So here again, I'm using this kind of universal set somewhere of A union B, right? So or sort of corresponds to union, is equal, now instead of equivalent, to the negation of A intersect the negation of B, right? So like that, as sets now, right? And this is because literally you can take these two things up here and you can say, well, we have this equality if we have x's in this side, if it's in that side. So this becomes, you know, x is in, not A union B, if and only if, you know, x is in, not A intersect not B. All right, and you can keep pushing that through. So what does it mean to be in the negation of A union B, right? Anyway, you can keep on pushing this through. The point is you can actually use truth tables, right, to verify set theoretic things, right? So if I want to verify a what was it? Yeah, this. If I want to, in fact, let me forget the union. So let me say I want to do this more general thing. So C minus. Sorry, let me not use that minus. Let me use C minus A union B, right? I want to show is the same as C minus A. Dang it. C minus A intersect C minus B, right? So I want to show something like that, right? And so in doing that, right, I can instead look at a truth table, which would be something like C, I guess it is a little tricky. Okay, maybe with negations, maybe I jumped the gun here a bit, but C and, right, the negation of, I'm going to just lowercase all the letters, A or B, right, I want to say is equivalent to C and the negation of A, and C and the negation of B. Oops, little b, because I'm changing it to propositional stuff now, right? So like that. Right, and we could do this by doing proof, right? So let's try to do it using a proof. So let me start with this side. So I have C and now I can use De Morgan's rule there, right? So not A or not B, right? And then I can say this is C and not A. Oh, sorry, an or here needs to change to an and, right? For De Morgan's law. So this is becomes C and not A. And this is actually not quite distributivity, but I just have C and stuff, right? So I can do and C anywhere here. So C and not A, and C and not B, right? Because you're really just intersecting them all in that case, or taking the conjunction of them all, right? In fact, this is kind of like this is actually sort of like a with like associativity in some sense, right? I can kind of, because these are just ands, right? I can kind of ignore the parentheses and move the C wherever I want it, and I can also kind of double up, like C and C is equivalent to C, right? Maybe this was more confusing. If I want to just do the truth table, so let me just go back and do the truth table instead, right? Then I have, you know, A, B, C, right? And then I have to figure out what these things are. So it's kind of a pain to do this truth table. Actually, let me, you know what? Actually, let me do this. I was going to show you this tool earlier, so let's just do this. Because this is a useful tool. So here's a tool that just does truth tables for you, which is kind of nice, right? Now you have to kind of look at the language and see how to, so I can use this like negation for this, like for not. Okay, I can use negation, or I can just type not. I haven't tried all the options here, so you might. Oh, I guess you can use the caret for and. Anyway, you can try typing things in various ways. But what I'm saying here is that C and how they have negation. A, how they or B is equivalent. So so I can apparently just write equal to C and not A, and C and not B. And let me see if this works. Unknown operator minus. Oh, I didn't like the minus. What was the? Oh, I see. Sorry. Yeah, no, I can use this bang. I guess we call this bang. All right, for not. Let's try that. There we go. And so we get this big old truth table here. Let's expand it. And notice that for my final thing, I get true, 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 right? So this is a tautology, which is what we needed to see, right? So that's good. So this is a useful tool for generating truth, because truth tables are just kind of a pain to make, right? Because this did all the rows for me and everything. So anyway, it's a tool you can use to play with if you want to play with some truth tables. There's many others too. That was like one of the first three that popped up. That's how I generated this truth table. It's right here. Let's see what else in sets. So we've got the algebra of sets, functions. Okay, so oh, we have some more things, like we can do A cross products. So this is just useful to know, right? So A cross B is a set of ordered pairs, A and B. So, you know, like we could go on and on, right? What's an ordered pair? It's different from a set because order matters, right? So 1, 1 in an ordered pair is different from 1, right? Let's I'm just going to pretend you understand that, and then I have A and B and B, right? And we can kind of view this, whoops, as a set, and we can kind of view this like you do in algebra, we can say we have A there and we have B there, right? And I have an object, A there and B here, and I have my, point AB, right? So you can even kind of view it like this in a way. Even though these don't have to be orders or anything else. I mean, just arbitrary sets. And then of course we have the notion of functions, right? F going from A to B, right? And I'm going through this fast because you probably all teach this in algebra classes. But this basically means F is a subset of A cross B as a relation, right? And it has the property that for all x in A, there is some y in B, right? Such that f x y, right? So there's something, right? And this is saying the domain of f is A, right? And it also says for all x in A, how do I want to say this? For all y prime in B, right? If fxy and fxy prime, then y equals y prime, right? So there can only be one value for an x, right? So that's the single valuedness of a function, right? And so these are sort of the two ways we say, so if those two things hold, we say that we have a function. This relation is a function, right? And then instead of writing fxy, we usually write, f of x equals y, right? So we're familiar with what functions are. So that's kind of how they're formulated in set theory. And we do this in algebra classes too, right? And then if you have sets, right, I can say f of, some set, I'm using A and B. So again, let me sort of fix this. So I've got my f, and now if f satisfies those things, I say I have a function from A to B, right? Keep in mind that this means that the domain is A, right? There's everything. There's not like elements of A that aren't the domain of F. This means the domain is A in this notation. This is sometimes called the codomain. Now it doesn't have to be the range, right? The range may be smaller. But when we write this is the domain. Now that might differ from the way some of you teach calculus or algebra in high school or something. If we have some subset, right, of A, I can just define also f of c, right? So this is going to be all the image of things in C. So this will be f of x for x in C, right? So where does this set get moved to in B, right? And you can also define like f minus 1. So let's say I have some D subset of B, right? So f minus 1 of D will be the set of all x, right, in A, right? Such that f of x is in D, right? So it's like the pre-image of D, right? So anyway, just common notations, right? So we use notations like that all the time. Finally, cardinality, just really, really quick. So it just means the size of a set. So for finite sets, it's kind of clear, right? For a finite set, you have n elements, or 12 or 13 or something like that, right? But for infinite sets, it's a little bit trickier, right? So in general, we define set A has size. This means the size of A is smaller than the size of B. If and only if there's a function f going from A to B, and f is 1-to-1. It's injective, right? So in other words, if I have all my points here in A and I've got B, and I can, in a 1-to-1 way, match up points from here into there, right? Maybe the range is some subset, right? Then I've just used up those points in a 1-to-1 way, right? Onto a subset of B, then we'd clearly say that this set has size less than or equal to B. Kind of something that's equivalent, but is a little harder to prove is equivalent, is that that we might say A has size less than or equal to B, if and only if, in fact, I'm going to put a star here because it's not immediately clear that these are equivalent. There exists an f from B onto A. So f from B to A, and f is onto is surjective. Okay. Now it's actually true. Now here we jump into some higher math. If the axiom of choice holds, whatever that is, that A is less than or equal to B, if and only if A is less than or equal to star B. Okay, so they're actually equivalent. And without worrying about what the axiom of choice is or how this is proved, I mean, because this isn't completely trivial to prove. You're trying to say, if I have an injective map, so one direction is pretty easy. If I have an injective map from A to B, I can clearly get an onto map from B to A. I just take all these points that weren't mapped onto and just pick something and map them all onto it, right? But the other direction is not so clear. If I have a map onto A from B, it's not quite so clear how to get a map one-to-one from A into B, right? So it's not quite as clear that direction. It's not so hard. It's actually interesting because we can talk about equivalence relations and equivalence classes, but we could go on and on with all this stuff. But anyway, some things required here. But it's kind of useful to have this equivalence, right? So if I want to show one set smaller than the other, sometimes it's easier to show that I have an injection. Sometimes it's easier to show that I have a surjection, right? Like if I want to show Q, right, has size less than or equal to Z, right? So these are the rationals, these are the integers. Well, according to this, all I need is a surjection from Q onto Z. Well, that's easy, right? Because Z just sits inside of Q, right? So I can clearly surjectively map Q onto Z, right? On the other hand, same argument, right? It seems to be the same argument. We're going to argue the reverse direction, right? So that's actually the star version. Is less than or equal to Q because I can, in a one-to-one way, map Z into Q. And well, that's obvious. I just map Z into Q by taking I to I, right? So I seem to be using the same argument for both directions of this, right? And then the upshot is that I get Z has the same size in terms of sets as Q, right? They're both what we call countably infinite sets. So this is useful, and this is called the Schroeder-Bernstein theorem. So it's got a name. And again, I'm not terribly interested in how the proof goes here, right? I mean, if anyone's interested, we can talk more about it. But that's just sort of a brief little bit of set theory. And so the final section will be a little bit about proof techniques. And I'll just go through some examples. There's many proof techniques and whole books on proof techniques. So I'll just do a few examples there. And of course, you'll get better at all this stuff once you get into classes where you're doing lots of proofs and you start doing them, right? And reading, right? Reading proofs, one thing when you're reading your math, you should try to do the proofs while you're reading it yourself, right? And then when you get stuck, read a little bit further, right? See how whoever's writing the proof proceeds, right? And then keep going. And sometimes you'll find that it's easier to just come up with your own proof than it is to read someone else's, right? I mean, you might know this from grading. Sometimes it's hard to grade papers because what the student's doing is correct, but it's not quite what you would do, and it makes it kind of difficult to figure out what's going on sometimes. But that's pretty common. Anyway, that's it for this section.